Hello everyone, welcome back. This is sort of a follow-up to the last video that I made, in that I'm continuing on with the theme of looking at groups as groupoids with one object. And specifically today, we're going to be linking one of the most fundamental theorems in category theory with one of the most fundamental theorems in group theory, and that is that we're going to be showing that Cayleys theorem, which says that every group is a subgroup of a symmetric group, and we're going to be showing that Cayleys theorem follows from the Yoneda lemma. And the Yoneda lemma is something I made a video on where I proved it in some theorem of the week, a year or two ago. So if you want details on the Yoneda lemma, then check out that video. And actually I clicked on that video and the top comment that I pinned it was also really good, so and he actually mentions Cayleys theorem in that top comment. But anyway, back to the video at hand. We're going to be showing that Cayleys theorem follows from the Yoneda lemma. So in this video, the version of Yoneda's lemma that we're going to need, so I won't be stating it in its full generality, just the version that we'll need, is that if we're in a category C with some objects A and B, then the set of all natural transformations between the Hom set of A and B, this is isomorphic to just the set of all maps from A to B. So this is the statement that we're going to be needing, and in particular, let's have a look at this. So, let's just apply it to what we have already. So, if we let A and B be the same thing, then we have that the natural transformations between the Hom set of A and itself is in bijection with the set of maps from A to A. Now, if we apply this to the groupoid with one object, what we're saying is that the Hom set, or between the one object and itself, so the set of all maps from the object to itself, is in bijection with the set of natural transformations between the Hom set of the one point and itself. But now, if you recall from last time, the elements of our group are precisely just the maps from the one object to itself. Sorry, I shouldn't say map, the morphisms from the singular object in our groupoid to itself. And so we're saying that our group G is isomorphic to the set of all natural transformations between the Hom set and itself. So what we really need to understand is, what are these natural transformations? And to do this, we shall say, okay, well, indeed, natural transformations are actually examples of functors within the category of functors. So if we instead look at this set as if we consider the category of functors between the opposite category of G and set, then the Yoneda lemma gives us an embedding. So it gives us a map which goes from G into this set. And how does it do that? Well, it will so we have a map from G into our set. And what does it do? Well, it will take the singular object, we'll call this one Y for Yoneda embedding. So Y will take the object of G to the Hom set of that one point. And remember that this is an object in our category here because this acts as a functor, so it is an object in this category. And what does it do to morphisms, aka elements of G? Well, it will take YG, will be sent to the natural transformation between our two Hom sets, like so. And how does this act? Well, what it does is it's basically multiplication on the left, right? So if you think about it, if we were to apply this to a map F, so say we have a morphism F from star to star, from the one object to the one object, then Hom Hom G applied to F, well, it will still map from the point to the point because that's the only option we have. But this time what it will do is it acts by multiplication on the left. And what we can see is when we look at this Yoneda embedding, is that actually these, in this case I'm calling them morphisms because in the category of functors they're morphisms. Also I should probably denote this more properly like that. Anyway, they form a group, and why is that? Well, YE will be the identity transformation, the identity functor, because if you compose by E on either side, you just get your same morphism back because, again, the morphisms are just elements of a group. Secondly, if you look at this definition, associativity is quite clear. You know, we can compose these and we're associative, it's fine. Now, inverses, well, the inverse of YG will just be YG inverse because YG is a functor, so YG composed with YG inverse is equal to Y of G composed G inverse, which is equal to YE, which is the identity. So we have inverses, we have an identity, we have associativity, and I think closure is quite clear as well. So these natural transformations, which we're viewing as functors between, as morphisms between functors, if you will, in the functor category, these natural transformations actually form a group. And so, okay, good. So now we have our group G is isomorphic to some group which is given by these YGs. But what actually is this group? Well, okay, let's have a look. So an element of the form YG is mapping you from this Hom set to itself. But remember, this is really just mapping you from G to G. And, well, what is this? Sorry, yeah, and what is this map? Well, this map is precisely given by multiplication on the left. So in other words, it's y is sending you from, if we're putting it in group theory terms now, sending you from G to G, sorry, yg is sending you from G to G, and it is taking an element x and acting by multiplying on the left. And so, in other words, this, the group of such maps yg, this, so I'll put it like this, is a subset of the symmetric group of G. Why is that? Well, because these maps here are indeed permutations of G. We can see that we need to show that these maps are bijective. Well, we know that it's surjective because if you plug in E, sorry, yeah, because any element of G can be mapped to in this way by just doing, say we want to map to an element H, we just set X to be G inverse H, we get there. So it's a surjection, and we know that it's an injection because if we had Gx equals to Gx prime, then we just multiply on the left by G inverse, and we get that that X equals X prime. And so each of these elements of our group, which we know is a group, is a permutation of G. And we also know by the Yoneda lemma that this group of permutations is isomorphic to G. And so we have Cayleys theorem. We've shown Cayleys theorem, which is that G is isomorphic to H, where H is a subgroup of the symmetric group of G. And yeah, so indeed, what we've shown is that Cayleys theorem is actually a special case of the Yoneda lemma when you apply the Yoneda lemma to the groupoid with one element, with one object, sorry. And yeah, and this is nice because, yeah, it kind of shows that you could argue that the Yoneda lemma is a vast generalization of Cayleys theorem. And I believe that sort of you can do a very similar thing with rings or other algebraic objects, and you can apply the Yoneda lemma to it, and this kind of gives you a universal way of arguing about results like these. But anyway, yeah, I enjoyed filming this. I enjoyed learning that the Yoneda lemma actually does just imply Cayleys theorem. And if you enjoyed that, then yeah, I hope you stick around for the next video. Cool, I'll see you soon.